Hey everyone, this is part 2 of acids and bases. It's supposed to be chapter 8, but that's really a lie. This information that you're going to see in this video comes from chapter 1. We kind of skipped over it when we went through chapter 1. It's on pages 26 through 28. So just take note of that. All right, let's get started. Since we're going to start talking about equilibriums a lot, we should define what equilibrium constant really means. We skipped over this chapter at the beginning of the semester because I wanted to wait till we started actually talking about chemical equilibrium. So equilibrium describes the state, quote unquote, if you wait long enough. Most reactions of interest in analytical chemistry reach equilibrium in times from fractions of a second to many minutes to possibly hours, not sure, but they do range in time. So for a reaction that has reactants A and B, and those reactants A and B are converted to products C and D, we write the equilibrium constant of that reaction as K is equal to concentrations of the products over the concentrations of the reactants. Now notice the small superscript letters denote the stoichiometric coefficients in front of each of those components. So in other words, the symbol A, right, in brackets, stands for the concentration of A relative to its standard state, which I'm going to talk about later. If the reaction is favored, the value of K, of the equilibrium, is greater than 1. So that's how you know if reactions are favored or not favored. All right, so each quantity is expressed as the ratio of its concentration to its concentration in its standard state. What does that mean? Well, for solutes, the standard state is 1 molar. For gases, the standard state is 1 bar, which is close to 1 atm. For solids and liquids, the standard states are the pure solid or the pure liquid. So even though in reality, when we write bracket A, like saying the concentration of A, what we really mean is that the concentration of A is over 1 molar. But we never write that. That's rarely written like that, so don't stress out. It's just you have to know that. So when we write the concentration of A, that bracket A, that's really saying over 1 molar. If we say that it's a gas, we have to realize that it's over 1 bar. Okay, so the concentration of that gas, so let's say that the term D is a gas, then we would really mean is that the concentration of D in that solution, or I'm sorry, in that reaction is over 1 bar. To emphasize the fact that it is a gas, we actually write it instead like how you see here, PD. So instead of having bracket, D, close bracket, we would actually write P, and then the component is used as a subscript. That really lets us know that, okay, that's a gas. So it's kind of to not get us confused. So again, how do we write equilibrium constants? They're products over reactants. If you have a pure liquid or a pure solid in your reaction, then the standard state is actually unity, because that standard state is the pure liquid or the pure solid. It's the most standard state of that component, right? So if it's a pure liquid or it's a pure solid, we don't use them. We don't put them in the equilibrium equation. And again, the reason that is because the concentration is so close to that of the pure liquid or of the pure solid that the value of the concentration is essentially 1. So you don't use it. It's called their unity. This is the basis of equilibrium constants. There is one thing to remember. Each term in the equilibrium constant is dimensionless because each of the units actually cancel. It's a ratio. But when you specify the concentrations, you're going to use the units of molar, right, of molarity for solids, or of bar for when you're talking about gases. So just realize that. That's why when you saw the kW, that 1.0 times 10 to the negative 14th didn't have an m at the end, because we were just talking about the equilibrium constant. But when we start talking about concentrations, when we start specifying concentrations, now we got to throw in the molarity, because that's what they're defined as for equilibrium constants. They're over 1 molar. All right. So what is the take-home message? The take-home message for equilibrium constants is the concentrations of solutes are expressed in moles per liter, in molarity. The concentration of gases are expressed in bars. The concentrations of pure solids, pure liquids, and solvents, I didn't mention solvents before, but as solvents as well, are omitted because they are considered unity. They're so close to the standard state that they're considered one. So they're considered unity, so they're omitted from the equilibrium equation. Now that we know how to do the equilibrium constants, we have to learn how to manipulate them. Let's consider the reaction HA is in equilibrium with H plus and A minus. If we wanted to write the equilibrium constant, we would put products over reactants. And as you see there, it's H plus times A minus over HA. That makes sense. Now, what if the reaction is reversed? What would the equilibrium constant be? If K is the equilibrium constant of the normal, of the forward reaction, then we would say that K prime is the equilibrium constant of the backwards reaction. So all you got to do is take whatever you have for K and take the inverse of it. Don't get confused if we give you problems that will say, okay, here's the forward reaction. I want you to give me the equilibrium constant of the backwards reaction, of the reverse reaction. All you got to do is do the K, but then take the inverse of it. And that would be your K prime. All right, well, what if the reactions are, what if different reactions are added? So then now you have HA, the first reaction is the same one that we just saw. HA is in equilibrium with H plus and A minus. That would be your K1. And then you have another reaction. Let's say H plus C is in equilibrium with CH plus. Okay, so you take the equilibrium of that one, K2. And then you have the sum of the reactions. That would be your K3. So if your reactions are added, the new K is the product of the original equilibrium constants. To convince yourself that all this cancels out, because basically what you're doing is you're adding things, you're adding reactions up. Notice that the H plus in K1 and K2 cancel out. So what you're left with is HA plus C plus A minus plus CH plus. So let's do an example to make sure that we understand. From the equilibria, you've got the first reaction is water, the second reaction is ammonia and water, and you see the K of the equilibrium constant of water. Notice again that here, for the equilibrium constant of water, we don't do over the pure liquid, right? We didn't understand that before in the other video, but now we do, because it's a pure liquid, so it's unity, so we don't include it in the equilibrium equation. So you have the equilibrium constant of the first reaction, and you have the equilibrium constant of the second reaction. So first, we notice that this third reaction comes from the original two reactions. The first reaction has H plus, and in our final reaction that we're looking for, we have H plus too, and it happens to be on the right, on the correct side. So we leave the Kw exactly how it is for the H plus. The next two things are the NH4 and the NH3. You notice that in the second reaction, we have those same two things, but they're on opposite sides of each other. So let's go ahead and flip that second reaction. So now it would read NH4 plus OH minus is in equilibrium with NH3 plus H2O. If you do that, you notice that your OHs cancel and your waters cancel. And you end up with the reaction that they want you to find the equilibrium constant for. Now we got to figure out, okay, so whatever we did to our reactions, we have to manipulate our Ks, our K values. So the first reaction, we didn't do anything to it. So it stays as 1.0 times 10 to the negative 14th. Now, K2, right, the second reaction, we reversed it. Remember, when we reverse the reaction, we take the inverse of it. So all we're doing to find K3, or the final equilibrium constant, would be 1.0 times 10 to the negative 14th times the inverse of 1.8 times 10 to the negative 5. If you do that, you should get 5.6 times 10 to the negative 10th. That is how you manipulate equilibrium constants. All right, guys, that does it for this video. I am going to resume with Chapter 8, for real this time, strengths of acids and bases. All right, see you later.